All right, welcome. In this explainer, we're going to build a complete, exam-focused understanding of a seriously powerful classifier in machine learning, the support vector machine, or SVM for short. So, here's the game plan for mastering SVM. We're going to start with the big ideas, then get our hands dirty with a real example and some code, and we'll wrap it all up with a super focused review for your exam. Okay, let's dive right in. First things first. What exactly is an SVM, and what problem is it even trying to solve? So imagine we've got two groups of data, these red and yellow dots here. The main challenge is to separate them. But as you can see, right, there are literally infinite possible lines we could draw to split them up. So that's the big question, isn't it? Out of all these options, how in the world do we pick the single best one? Well, that's exactly the problem SVM was designed to crack. So SVM's answer to this puzzle is something called the hyperplane. It's just a fancy word for the decision boundary. And it's defined by this equation. Now, don't let the math scare you. It's pretty straightforward. X is just our data point. Think of W as the weights. Tweaking them is like tilting or rotating the line. And B, that's the bias. It just slides the whole line up or down without changing its angle. The whole goal is to find the perfect W and B to create the best possible line. Okay, all that theory is great, but let's make it real. We're going to walk through a super simple email classification example. This is where it'll all click, I promise. Imagine we're sorting emails. On the x-axis, we have the number of business words, and on the y-axis, the number of emojis. The blue dots, those are our work emails, and the green squares are personal emails. You can see the pattern, right? The job for our SVM is to draw the perfect line to separate these two groups. Okay, so after the model trains, it figures out the best possible weights and bias. For this specific data, it learned that the weight for business words should be -1, the weight for emojis should be +1, and the bias is 0. So how do we use this? Let's take a new email that has 1 business word and 2 emojis. We just plug those numbers into our formula. That's -1 times 1 plus 1 times 2, which gives us a score of +1. And here's the rule. A positive score means it's a personal email. A negative score? That's a work email. Super simple. And if we run that same function on all of our data points, you can see it works perfectly. Look at the pattern here. Every single work email gets a negative score, and every personal email gets a +1. Our hyperplane is doing its job beautifully. Okay, so we have a line that works, but how does SVM make sure it's the absolute best line? And this next part is absolutely critical, especially for your exams. Okay, so this is the absolute genius of SVM. It doesn't settle for just any line that separates the data. No, it finds the one line that creates the widest possible street, or margin, between the two classes. And why do we care? Well, a wider margin is like having a bigger buffer zone. It means the model is more robust, more confident, and it's much less likely to mess up when it sees new data it's never encountered before. Now, take a look at the data points that are right on the edge of that margin. The ones almost touching the line. These guys have a special name. They're called support vectors. And here's what's so cool about them. They are the only points that matter. Seriously, you could delete all the other data points, and as long as these support vectors stay put, the hyperplane won't change one bit. The entire model is literally supported by these few critical points. Okay, that's great for data that's easy to separate. But what happens when a straight line just won't cut it? Well, this is where SVM pulls out its secret weapon. Yeah, in the real world, data is often messy. It can look something like this, all tangled up. You can see that a simple straight line would be a total failure here, right? It would misclassify a ton of points. So to solve this, SVM uses its famous kernel trick. It's a really clever mathematical shortcut. Instead of trying to draw a crazy, curvy line in our 2D space, the kernel trick basically says, hey, what if we could project this data into a higher dimension, like 3D? The magic is that in that higher dimension, the data might suddenly become easy to separate with just a simple flat plane. You can really see it in action here. On the left, you've got our tangled 2D mess, but then the kernel trick does its thing, and boom, on the right, it's projected into 3D space. By adding that extra dimension, it's like we've lifted one class of points up, and now slicing between them with a flat plane is super easy. And here's the final piece of the puzzle. When we take that simple flat plane from our 3D view and project it back down to our original 2D graph, it becomes the complex, perfectly curved boundary that we needed all along. That's the kernel trick.
It's an elegant solution to a really messy problem.
All right, theory's done. Now it's time to see how this all works in the real world. We're going to step through a coding lab using the Breast Cancer Wisconsin dataset to see a real SVM in action.
For this lab, we're using a classic dataset, the Wisconsin Breast Cancer Dataset. We have data on 569 tumors with 30 different features for each one, things like tumor size and texture. Our goal is simple: classify each tumor as either malignant or benign.
And we're going to follow a totally standard machine learning workflow here. We'll load up the data, split it into training and testing sets, and then, and this is the cool part, we're actually going to build two models to compare: a basic linear SVM and a more powerful one using that RBF kernel we just talked about. So after running the code, here's what we find. Now, both models did a fantastic job, but if you look closely, the RBF kernel SVM has a slight advantage across the board in accuracy, recall, and even the cross-validation score. So what does that tell us? It's a strong hint that the relationships between all those 30 features aren't perfectly simple and linear. The RBF kernel, with its ability to create a more flexible boundary, was just a little bit better at capturing those complex patterns.
Okay, let's bring it all home. We're going to do a lightning-fast review of the absolute must-know points for your exam. This is the stuff you need to lock in.
All right, deep breath. Here are the key takeaways. Number 1, the goal of SVM: find the best hyperplane by making the margin as wide as possible. 2, that hyperplane is held in place only by the support vectors, those critical points on the edge. And 3, when data is messy and nonlinear, the kernel trick is our hero. It bumps the data up to a higher dimension to find a simple separation. You get those 3 things, and you're in fantastic shape for your exam. And you know, this incredible technique goes way beyond just sorting emails or analyzing medical data. It's the engine behind things like facial recognition, text classification, and even bioinformatics, which really leaves us with a final, bigger question to think about. In a world full of complex data, where else could finding that one perfect dividing line change everything?